It's my pleasure to introduce this next session of talks, our concluding session for the day. As a reminder, immediately following this session, there will be two fun things simultaneously in the same spot, a happy hour and a poster session. So please stay and engage in conversation with folks presenting posters during the happy hour. For this next session, our first speaker is David Elkind, who is a senior data scientist at CrowdStrike. And as you know, as you can tell, he has Beamer slides, so he knows what's up about creating slides for mathematical content. He holds a Master's of Science degree from Georgetown University, and his talk is about mitigating adversarial attacks in machine learning. David.
Thank you. So I walked through a proposal for how to make models more robust to different kinds of adversarial evasion. Oh, yeah, thanks, man. A couple of experiments demonstrating how it works, and hopefully some intuition that makes the regularization plausible as like why it actually becomes more robust. So, as we all know, static analysis of PE files is pretty easily evaded. You can do all sorts of stuff to a file. You can append data. You can do sections, and that will confuse any feature-based or even non-feature-based machine learning methods. So we want to be more robust to that because customers don't buy products that don't work. Even unsophisticated stuff like appending an ASCII byte to an overlay can make a file evasive, and that's not really that encouraging because any moron can do that. So I developed this regularization strategy that encourages neural networks to ignore these kinds of chaff modifications. This appended data shouldn't actually influence how the model works because it doesn't actually change how the malware works. It just is sort of a disguise. It's like putting a dog in a hot dog costume. So for a pair of files, we take an ordinary sample and then we append some ASCII text to the end of it. And we want the neural network to treat those two things as the same. So we just introduced this norm regularization on the end there. It looks kind of like L2 regularization a little bit. The idea is just that every software sample gets a twin. And then we regularize the model to treat the twins the same way because adding the ASCII text doesn't change it. It should be the same. Why do we want to do this? Well, adversaries make the malware, and they're not going to be nice about it. So everything that they can do to a PE file is under their control. We don't want to cede that terrain to them, so we need a way to be more robust. If we remove every feature the adversary can modify, then we're left with pretty much nothing, maybe almost nothing, right? Because every element of the file is under control. So we have to make models that are smarter and models that are robust even if they're under attack. So we want them to be treated the same. We call this pairwise hidden regularization. So the intuition here is that nothing has changed. It's the same file, it just has some shit on the end. So we're going to treat those two things as the same by adding this regularization penalty. And we apply it we can apply it to every hidden layer, we can apply it to one or two hidden layers. They end up working more or less the same even if you don't do it at every layer. We know that the model will treat the two things as the same because this penalty is minimized at 0 whenever the hidden representations for the modified and the non-modified file are the same, right? So whenever these two vectors are the same, you've achieved your minimum of 0. The model is not confused at all because they're treated the same way. Nothing about what this research is particular ASCII bytes. It's just a useful, motivating example because I can explain it really easily. It's very cheap to do to a file because you don't have to do any PE parsing. And it doesn't break the fragile tooling, which actually ended up being a bit of a problem. Modifying a file using Leaf, you actually can break it sometimes, like inserting a section or just adding a new import, things like that. I don't really understand what's going on because intuitively the file hasn't been changed in a key way. But the problem is that you modify the file with Leaf and then you pass that to Ember. You try to get the features extracted, but Ember says, no, this isn't a valid PE file, and it stops working. And this is very upsetting. I filed a ticket my colleague filed a ticket to GitHub, but we haven't heard back, unfortunately. It's not a criticism of anyone, but we want to do this kind of security research, so we need like a little bit more robust tooling that doesn't fail when you do things like parse a file and then just write it, right? We eventually realized that it's not even appending stuff that causes it to break. It's just you parse it and then you write it back to a file and it's broken. I don't know why. So we want the neural network to have like a consistent way of thinking about files, right? We don't want to get confused by the extra data you've added to the end of it or the extra sections you've inserted. So I chose this regularizer. You can think about all sorts of different regularizers that kind of have the same flavor, right? Anytime you take a difference of this comparison of the twin files, That could be useful, but I think that this one makes more sense, and here's why. If you compare just the probability outputs, right, you take your sigmoid nonlinearity applied to the affine transform of the hidden representation, that's also kind of compelling, right, because they should have the same probability scores. The problem with this is it's going to suppress the actual information that you care about, and that's because it's a sigmoid transform, so it's got saturated nonlinearities. It can be very different, but it will have a very small difference, right? If you're in the tail end at either point on the sigmoid, it can be a very large distance, but it'll be treated like a very small difference. Whereas here, that's not going to happen. It's not going to be saturated at the ends. The other thing is that the twins usually end up on the same side of the nonlinearity. So if it's a malware, it's going to be close to 1. If it's clean, it's going to be close to 0. What that means is that you've already got your loss function to penalize it for being incorrect, right? They're never going to be opposite, or they shouldn't be. Goodness, I hope they're not opposite, right? I'm not sure this is landing, but this is why I chose the penalty. So the experiment's really simple, right? Take the Ember 2017 data set, build a very small network, right? 256 hidden units, 1 residual connection, not a fancy network. Train it until an early stopping condition triggers, and then just compare the baseline model, where we do not apply regularization, to the robust model, where we applied this novel regularization method. Both models will train on pairs of modified and non-modified samples. So they both have like the data augmentation effect present. Then we just, whenever we need a classification decision, I used a ROC curve to pick the FPR at 10 to the negative 3, and that's our cutoff, right? We want to achieve a good trade-off between false positives and true positives. So just to be clear, this does not have any bearing on any product that CrowdStrike releases. This is purely just a toy model, so these are not demonstrating like how to actually evade real models that we actually use. So just sanity check, does using this regularization penalty encourage the norm of the difference to be smaller? The answer is yes. The blue is the model with a novel regularization. You can see that smoothing line is consistently lower than the non-modified, or than the baseline model. So the model is actually encouraged to think about these two things the same way. What this says is that when you modify a sample and then you pass it to the baseline model, it's picking up that noise that you've added, and that's causing a discrepancy between how it treats the file and the file that's been modified. And that's where your errors come from. That's why it becomes evasive, is the model is being tricked by that added data. Okay, so experiment 1. We apply large modifications to a file. For every file in the data set, we take the feature vector of the original file, then we append some random data. We try to get a large penalty, or not a large penalty, a large difference in the feature vector, just because we want the data we're training on to be very different, right? If there's a small difference, that's not really meaningful from the perspective of the model. So we want to make the two files very different. Does it actually work? Turns out the answer is yes. At some levels of penalization, smaller values of penalization, it turns out that the model is much more robust because there are a higher true positive rate. We're missing fewer files in our test set compared to the baseline model shown in blue. But if you set lambda too large, you'd end up making the model worse. Why does that happen? Well, it's the same reason that every other model gets worse when you apply too much regularization, right? You're making the model not able to fit the data well. This same pattern appears in other metrics as well. ROC curve, accuracy, log likelihood, consistently better for lower levels of regularization, getting worse as you apply larger values of regularization. This is just pretty common bias variance trade-off stuff, right? Okay, experiment 2. How hard is it to evade the regularized model? So we're doing a similar thing. We take a sample, append some data, and see how many attempts it takes to evade it. The point of experiment 2 is just to test whether or not it's easy to find an evasive sample. This is closer to what an adversary is actually trying to do, right? They don't care about whether or not the feature vectors are different. They care about how easily can we find a sample that is evasive for any given input, any input malware. So this is a different test set, right? It's not restricted to have large distortions, and for each model, a different set of modified files is created. That's the difference in experiment 2. Still works. For each of the 100,000 malware samples in the test partition, we did feature extraction, and if a sample is detected, we make 5 more attempts to modify the sample to evade detection. But our true positive rate is still really high. much better than the baseline model. Experiment 3. Does the regularization change the detection rate of non-modified files? So, if we add this regularization, do we get better or worse when we look at non-modified samples in the corpus? It's possible that the regularization is really good at detecting modified, but not the non-modified. Intuitively, the expectation is that the performance should be the same when you have non-modified samples, because we want the model to think about the modified and non-modified the same way. We've already shown that the norms are smaller when you apply the regularization. So our intuition is that these should end up being correct, that these should end up matching. And our intuition is basically correct. The modified samples are shown in blue, and the non-modified are shown in yellow. This might be faint, but all the dots are basically right on top of each other. If I included the statistical intervals, you would not be able to really see any of the content on this graph, but they're extremely close. This tells us that we're not trading performance in this sense. We're not losing any ground on the non-modified samples. So this is just this project was a toy to demonstrate, does this regularization method have value? Does it work on certain kinds of chaff data when that chaff is the very simple modification of ASCII text? Excuse me. But there's a lot of more work we can do with this. We can extend it to determine if some sequences of bytes that are not just random ASCII characters are more evasive than other sequences. This is basically what Fleshman did at DEF CON 2019 when he found a way to make every single example in the test problem evasive against 3 different models. Basically finding that if you add like Microsoft EULA strings and things like that, nature to a file, those tend to be very evasive strings because no one's going to classify Microsoft file as dirty. That's a pretty big flaw with how machine learning works. So we would like to see if this applies more generally to more specified and targeted string attacks. So there are also lots of different ways you can modify a file otherwise. You can add sections, you can add imports, you can add chaff data inside of existing sections, you can add an entry point that points at the previous entry point. There's lots of options that you can apply. My assumption would be that this method will also work, but we would need better tooling in order to test that very thoroughly. You can also apply sequences of different modifications. So can you add like a chain of different modifications on top of each other and then it become evasive? You can also generalize beyond pairs, right? And here we just have the original file and the file with ASCII text appended to it. Now imagine you have a triplet where you have a third modification like adding a section or adding another import. You'd want all 3 of those things to have the same hidden representation. It's probably going to be more complicated to regularize that because it's not just a simple difference. But there are lots of ways you can attack a model, and we want to have some sort of coherent way of thinking about how to get neural networks to consider all those different variations and varieties of attack as being the same thing. Because ultimately the underlying malware has the same functionality. It's still malicious, even though it's presented in a different way. Of course, this method is creating a static corpus, and we're just reloading that same data over and over again. A more realistic attack would be to present the model with alternative hard examples every time. Kind of like hard negative mining, if you've ever done like triplet sampling or triplet losses. The idea is that you want to generate online a hard sample for the model to try to detect. But that loop is long and complicated. So there's some suggestions of other ways you can make evasive files in this Anderson article from 2018 where they made a reinforcement learning agent. These are other things that other people should look, that people like me or you should look at if you want to think of other ways to get at this evasive problem. And that's what I got. So if you all have questions.
Thank you for the talk. So do you consider a white box or a black box attacker?
Can you clarify how you're using that terminology?
So you are using regularization to make your system more robust, right?
That's right.
Against adversarial attacks. And the adversarial is doing FGSM kind of an attack to you? Or like, did you do any performance against how much an adversary, how robust improvement do you get? Like a fast gradient time method kind of an attack?
I didn't benchmark this against FGSM or other kinds of attacks. I had to cut slides about the alternative methods of adversarial attack.
Okay.
This method is focused on just modifying the problem space, whereas an FGSM would be focused on modifying the feature vector.
Okay.
The problem with a feature vector perspective is that feature vectors can be modified in a way that does not correspond to any real software sample because there are complex dependencies among the different features inside of the feature vector. So you're kind of like solving a Sudoku puzzle on a bus going the wrong way because there is no longer a correspondence between the feature vector and the underlying malware problem.
Okay. All right.
So like, if we modify the sample directly, then it has to be, and that is still a valid PE file, then it has to be the case that the feature vector derived from that modified malware sample is also like the real problem that we want to solve. But if you modify the feature vector itself, irrespective of any concern about it being an executable piece of software, then you kind of have drifted away from solving the underlying security problem. You're training your model to be robust to something that may not exist.
I'm going to work my way up here.
Well, thank you very much. This was beautiful. It was so simple and elegant that I'm still in awe. But I have a couple of questions. One is, when you were testing the robustness against evasion attacks, did you perform a single test for each sample or multiple tests?
Yeah, I didn't explain that very clearly when I was giving my my talk. The test for this experiment is that first you just see, is the sample detected, not detected? And then if it is detected, then you modify the sample by appending bytes. And if it's not detected, proceed to the next step. If it's detected, try again, see if you can get an evasive set of bytes again. And then you do this, I think 5 times? Yeah, 5 times. The idea is that you're kind of trying to simulate, like, an attacker wants to make this particular sample evasive by adding random data. How quickly can you do that? That's sort of the idea that we're trying to get at here.
And my second question is, did you ever think of or try regularizing, not regularizing all samples, but just part of the samples?
Regularizing just which samples?
Just part of the sample set, the training set. So you are perturbing every file in the training set and creating a twin, right?
Yep, yep.
Did you try perturbing only part of the training set and creating a twin for just part of the training set and see how well it works?
I didn't try that just because I didn't try that because you would want to get the hidden representation for each. So if you don't perturb some samples, then that regularization component would be 0. Right? So if you have the twins, and then you want to regularize by the hidden representation, what are you going to put in there if there's no second thing to compare it to? It would be either itself or it would be empty. Yeah. So you could leave it as 0, I guess. I don't know. I guess my question to you is, what problem are you trying to solve by doing it that way? It seems like there's a second question that you want to ask that you didn't get the chance to like develop or something.
No, my question was just what I asked.
Okay.
The problem I'm trying to solve is the complexity and the cost of creating twins, because not necessarily a single twin is going to be enough.
Yes, that's a good point.
You may need to train more than, well, one twin. There's going to be triplets or even more perturbed samples for data augmentation, and you may not need to do it for all samples.
Okay, so like it's more efficient that way. It's expedited training process. Okay, yeah, that could work.
So I had a question. So would you say like an underlying problem, one of the things that from an offensive perspective that's been exploited is on a defense perspective, it's very difficult to interpret the machine learning model. And so as a consequence, it's very difficult to basically the model the robustness. So for example, we had in the summertime, I think came out with Silence with the strings, how the malware was being packed with strings, and from the detector was able to pass it as benign, even though it was actually malware, and all that what was different was the string. So I'm just trying to ask, you think that's one of the fundamental problems, is that interpretability, that is what you're trying to exploit?
I don't think that this is an interpretability problem.
No. What I'm saying is that from the defensive perspective, your talk's on the offensive perspective, but my question is more on the defensive perspective. The reason why these types of things are like the reason why I think they're the possibility in terms of evasiveness is that the robustness. It's hard to understand what it's actually doing from the defensive perspective. So that opens up possibilities from the attacker to exploit those things. Like just like you're saying, adding different bytes, right? It's hard from a defensive perspective to understand how that impacts the model.
Okay, I see what you're saying.
Yeah. I just want to get your thoughts on that. Sorry.
Yeah. So thinking about the pipeline is you have some software, you extract the features, and then you put those features through the model. If you change the file in a simple way, like adding bytes, that actually causes a complex chain of events to modify the feature vector because the entropy will change, your 2D entropy histogram will change, file size will change, section and like subsequence entropes will change, and so that causes like a sort of a cascade, right, of things how the neural network thinks about that file to change as well. I would like to live in a world where the model can say like, okay, this is like this other sample I saw, so let's make it more like that and pretend this doesn't exist. And that's kind of the train we're getting at. It's not quite there, obviously, but it's on the trajectory.
Hi. I guess I'm trying to understand the practical implications of what you're saying. So to me, if we assume there are like infinite ways to modify a file to make it malicious, right? Then in some sense, this is already a reactive, right, approach?
Yes. I had cut a slide that talked about how this might not be a complete solution.
So in that sense, instead of trying to understand what they're actually doing, what about just purely retraining on newer variants of malware that's coming out, since that's also reactive? And how would that compare with you sort of explicitly saying, the adversary is using this technique, I will try to simulate all the additional complexity machinery that you're going to put in to react every time to an adversary who's changing their attack, right?
Yeah, so nothing about this stops you from doing retraining as well, right? It does mean that you have to anticipate, like in a hypothetical scenario, you have to anticipate every possible modification. On top of which, the modification that takes this form is sort of like a exercise you will see at a security conference, not necessarily the kind of evasion attack you would see in the wild, right? Because packing is probably a way easier way to obfuscate what you're doing. So it solves a problem. It does not solve the very broad set of problems that we want to solve. And it's also not exclusive.
But the question is this like a problem? I don't know. How is it worth solving this problem necessarily, right? Because
yes.
Because number of exploits will go up exponentially, and so you're gonna to continue this, right? You have this exploit, then you have this one, and then you have number of samples growing exponentially that you're trying to predictably, well, not really predictably,
yeah,
but predictably.
Yeah,
train,
absolutely.
Right?
So the world that I would like to live in, and that I would like to get to, is that we have a better way to anticipate where samples will go in the future. One of the downsides of the way that the publishing cycle works for like conferences and whatnot is that I submit an abstract for research that I did a year ago, which is this presentation, and I don't get to talk about all the cool stuff I'm doing like yesterday. So, stay tuned.
It seems also interesting to think that the same framework could do exactly what Constantine's suggesting, right? By changing your twin from appended ASCII to maybe an evolved variant within the same family. So that seems pretty cool.
Yeah, great idea. I really like it a lot. The one thing I'll just push back on a little bit with the FGSM stuff is that, in fact, there's been quite a few papers now about using FGSM to either put stuff in the appended bytes, basically to decide, what bytes are the optimal to put in to evade for the append. Actually, it's much stronger than the random case. Random case actually doesn't really work very well for robust models. The other thing is also there's slack bytes as well, which we've seen also is completely modifiable. Slack bytes being sort of those unused bytes due to the alignment of sections, right?
Absolutely.
So
slack bytes are, where's my last slide? One of the options available that Anderson outlined in the paper on reinforcement learning. But thank you for your suggestion on FGSM finding optimal bytes. That's a good thing to point out.
Hey, so I like the talk, and it's a really interesting idea. I'm trying to wrap my head around this. Do you have an understanding, and if somebody already asked something along those lines, just yell at me. Do you have an understanding of how much the regularization is helping here, or is it possible to just achieve the same thing with the normal loss and just data augmentation?
Yes, so we have the answer in the affirmative here because the model, where's that slide? Well, I lost it. Oh, yeah. So the baseline model is also trained on pairs. Okay. The only difference is that you set lambda to 0, right? Then the regularization term is null. But the baseline model is seeing all the pairs that are available to the regularized model. So we know for sure that this is because of the regularization.
Yeah, do you have a hypothesis as to what that regularization is forcing the model to do differently than the pair without the loss case?
Yes. So the hidden, all the way deep in the hidden layers, these two things are close together.
Okay.
Right? And because they're close together, the model is thinking about them in the same way. Whereas in the baseline model, it consistently has a larger divergence from the regularized model.
All right, thank you.
I think going back to FGSM, I'm still stuck there.
Okay.
So if you do adversarial training, meaning that you create those perturbations, add those malicious things with the correct labels, and that augment your system like that as a training augmentation, train on those adversarial samples, then your robustness will be much better. So you're going to see that, even if you attack it with a very large epsilon value, your model will be still good, and you're going to be more robust again. Like your accuracy will still be high. It's not going to go down because the adversarial attacks goes there.
Yeah,
so I think that would be a good next step.